Okay, this is the second half of lesson 7.3. So here's a situation where we're going to do the sampling distribution of the difference in two means. So yesterday we just did the sampling distribution of X bar of means, right? So now we're going to have the difference of two means, similar to what we did with difference of two proportions. So this data looks like the populations are both normal. They took a sample of boys and they took a sample of girls. I think different size groups, and that's okay that they took different size samples there. There's a unique case in that there's a small window, a couple of years there in middle school, when the girls are taller than the boys in a lot of cases, and that's the case here. Their average height is actually taller than the boys' height. So if you think about what we did yesterday, if we did this individually for each group, this is what it would look like, right? Well, it looks approximately normal because the population was normal. Even though the sample size wasn't 30, that's okay. We did a less than 10% condition in order to use the standard deviation formula for the sample there. And so we did that, got all the data, just like we did yesterday. So what do you do differently with means? So when we're doing the difference of two means, first thing, if each individual sampling distribution, boys and girls in this case, is both approximately normal, the difference will also be approximately normal. So that's the first thing you need to know. So if you can prove that each one individually are approximately normal, you're good to go. You've proven that both of them are. This is just saying what's each one of those points represent. The 1.41 inches there. That dot means they took a sample of a certain size, and then they just subtracted that particular girl minus the boy height there, and they got a difference of 1.41. And so each one of those is a difference in the sample means there, the mean average there. Okay. So standard deviation. This is a new formula, and I should change this. Let me see if I can change it real quick. Okay, now it's displaying the correct formula there. So remember that the formula for an individual was just standard deviation divided by the square root of n. Here we have a big square root there, and we're adding instead of subtracting. Even though we're finding the difference in the means, the standard deviation is going to grow larger, so we have to add those two up. You just plug in the numbers, and you get your standard deviation 1.55. Where you know it's normal, so now you can draw a normal curve if you needed to solve this problem. These are the official formulas. You can write them down. Again, two ways to prove normality with means. Maybe the population is normal, that works. Maybe use what's called the CLT, the central limit theorem, and the n value is greater than 30. That proves approximately normal as well. Means are pretty simple. You just subtract them. Standard deviation for differences, you have to use that formula. It's on your formula sheet. You don't have to memorize it. But interesting enough here at the bottom, I want to make sure you catch that. So in order to use the standard deviation formula, we have to check the less than 10% condition for both the boys and the girls. So both proportions, both ones you're finding the difference between. So you have to do the condition twice. We've talked about that before. If it passes those conditions, it's independent or independent enough for us to use those formulas. Okay, fast food restaurant like Chick-fil-A or something uses these kinds of automated filling machines to pour soft drinks. They just push a button and it goes. And they do this for small, medium, and large. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution. That's nice to know, with a mean of 27 and a standard deviation of 0.8. The medium one, again, is approximately normal, has a mean of 17, standard deviation of 0.5. There's always going to be some variation in any machine, really, for just about anything. So there's going to be some variation, not much, but there's a few ounces of variation there. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of the 20 cups filled using the large setting and 25 cups using the medium setting. So the notation there is X bar of the large cup minus X bar of the medium cup. I like to use L and M and not 1 and 2. If used to generic terms like 1 and 2, you would have to define what 1 means. 1 is the mean of the large cups. 2 is the mean of the small cups or medium cups. What's the shape? Because those are both populations are normal, then we can say that both of the sampling distributions are normal. Find the mean, so you just do the mean of X bar minus X bar L minus X bar M is going to be 27 minus 17, or 10. Make sure to put the ounces there, put the units, it just makes more sense. Calculate and interpret the, so let's just show you that one because it's hard to talk about. Notice the notation there, mu of X bar L minus X bar M is a subscript. And this one, because, now, honestly, I went ahead and checked the 10% condition here just because I thought we had to. I think it's because they're just producing an unlimited number of these. They never really stop, and it didn't have a time period that they were looking at. So I think that's why they didn't check the condition. Usually a really good idea to check that condition. And again, we're just plugging that new formula for difference of means for standard deviation. Okay, so now we have a mean and we have a standard deviation. Varies by about 0.2. So when you do interpret the this standard deviation number, 0.205, so you start, the difference in the large cup minus the medium cup. Make sure you tell the direction of it by which one's first. And the sample mean amounts of liquid typically vary by about 0.2 ounces from the true difference in means. So the word you might forget to put there, which is important, is the difference. So I know standard deviation is typical deviation from the mean. In this case, it's typical deviation from the difference in the mean. So that word is an important word to include in your interpretation. I would draw the normal curve if I'm doing this problem. So I would get out, let me see. Okay, so in this one, you can see that we could draw this. And so if I go out one standard deviation, if the standard deviation is 0.205, this would be 10.205. This would be like 9.795, and so forth. Now, the question says to go, is within 0.25. So 0.25 in either direction. So if I go, that's 10.25. That's a little bit more than one standard deviation. And then 9.75, a little bit more than one standard deviation that way. So kind of that's the shaded area. That's the lower bound. That's the upper bound. And so you just do your norm CDF, right? So get your calculator out, menu. So 652. Lower bound is 9.75. Upper bound 10.25. Mean is 10, standard deviation 0.205. And so there's a 0.77% chance of this happening, that the sample means are difference in the means is between there. Okay, one more problem just to try. You might want to stop it. Just try this on your own, work it out. I'll read it out to you. So the distribution of height for U.S. males follows a normal distribution with a mean of 69.3, standard deviation is 2.94. For adult females, also normal, the population is, with a mean of 63.8, standard deviation 2.8. Suppose the researcher selects a simple random sample of 30 males and simple random sample of 50 females. X bar M, which is males, minus X bar females, as be the difference in the sample mean heights. What's the shape of the sampling distribution? So because they're both, populations are both normal, the sampling distribution of these is going to be normal. The difference is going to be normal. Or you could say they both have a sample size of at least 30 there at a time, so that works as well. So either way, I think they did that first way. Find the mean of the sampling distribution. So the mean would be, I think we're doing males minus females, so that would be males was 69.3 minus 63.8, 5.5. Don't forget to put the inches there when you do it. Calculate and interpret the standard deviation of the sampling distribution. Okay, so calculate the standard deviation. So check the less than 10% condition. So samples of those sizes, 30 males and 50 females, is way less than the total population of US males and females. So it's way less than 10%. So we can apply the formula. Again, the formula here is square root of standard deviation squared of the males, 2.94 squared, divided by 30. That's the sample size for males. And the same thing with females. You add them up, square root the total, you get 0.667. We interpret that by saying the difference in the sample mean heights typically vary by about 0.667 inches from the true difference in means of 5.5. Difference in means is the important part of that. Last question, estimate the probability. So we're going to draw a normal curve there within 1 inch of the true means difference. So if the true mean difference was whatever it was, I think it was 5.5, then you're going to go one less than that, 4.5, one more than that, 6.5, and then the mean and standard deviation, plug them into norm CDF, and you get 0.8662. That's your lesson for today.